If you're using an oscilloscope to analyze weak, low-frequency signals, it's possible to measure down to the microvolt range. First, once you connect a probe, even with a short circuit, the scope is picking up a lot of noise, so you should turn on the bandwidth limit for low-frequency measurements. Second, the ground or common of any other equipment may have high-frequency noise compared to the scope ground. This will be picked up as common mode noise, so turn on the low-pass filter of the scope. It's set to 10 kHz low-pass. There. I'll be using a signal generator to produce a low-frequency square wave. It'll be producing a 100 Hz square wave that's 1 volt peak to peak. Turning on the signal and adjusting the scope, these spikes are caused by the filter. Filter off, filter on. Now I'll measure a very simple circuit. Here's a 10,000 ohm resistor in series with a 10 ohm resistor, so it divides the 1 volt signal by a factor of 1,000 to produce a 1 millivolt peak-to-peak signal. I'll increase the scope gain to its limit of 2 millivolts per division. It's fairly noisy, mostly with common mode noise. However, all the noise can be significantly reduced by using a differential amplifier. This amplifier is set to a gain of 10 and a bandwidth of 10 kHz. I'll plug the output of the amplifier into the scope. Connecting the 1 millivolt signal to the input of the amplifier, it's now amplified to 10 millivolts peak to peak. The differential amplifier independently amplifies both the 1 millivolt input and the ground, both by a factor of 10, and then subtracts them from each other. The signal is so clean that I can reduce it by a factor of 10 down to 100 microvolts, and I'll increase the amplifier gain to 100 to see it more clearly. I can even decrease the signal by another factor of 10 down to 10 microvolts peak to peak, and yet the signal to noise ratio is better than the 1 millivolt original signal. At this high gain, you'll encounter thermocouple effects. The metal of the clip and the prong are slightly different. If I warm up one clip with my finger, there's a voltage rise of about 10 microvolts. Warm up the other clip and there's a similar drop. These changes will recover to room temperature quickly, but temperature variation is a consideration with these small signals. There's another simpler way to connect a signal to a differential amplifier. Short circuit the negative input and connect the BNC with the full signal to the positive input. This means that the negative input is still amplifying the ground and subtracting it from the positive input. The output is not quite as clean this way, but it's easier to do quick connections to the amplifier. In order to eliminate common mode noise, as well as other interference, the LNA10 has two low noise amplifiers, positive phase and negative phase, each with an initial gain of 10. The two signals are subtracted from each other with precision better than 1 part in 100,000 to eliminate common mode noise. In addition, inline radio frequencies cause parasitic DC to appear in amplifiers. These two amplifiers have an RF crossover filter to cancel this effect. To demonstrate the noise elimination, I have a 1 kHz square wave at 1 volt peak to peak. This is reduced down to 1 millivolt peak to peak. Now the scope is set to a 1 megahertz low-pass filter, and there's a lot of high-frequency noise. Turning down the filter frequency to its lowest of 25 kHz, there's still obvious noise. Turning the frequency back up, I'll connect the LNA10 now, which is also set to a 1 megahertz low-pass filter. The gain is 10. I'll adjust the vertical down by a factor of 10 to show what the scope was actually seeing. Looking at just the positive input, this is why the scope was so noisy with a direct connection. And here's the ground signal. Subtracting them, you get a very clean signal. I'll increase the gain to 100. Again, the low-pass filter is set at 1 megahertz. So let's look at a 100 kilohertz square wave. As expected, it's slightly rounded. Returning to a 1 kilohertz, the LNA10 has a continuously adjustable low-pass filter, 1 megahertz to 100 kilohertz, 100 kilohertz to 10 kilohertz, 10 kilohertz to 1 kilohertz, 1 kilohertz to 100 hertz. It goes down to 1 hertz, which is flatline. The DC offset reference to the input can be increased or decreased by 1 millivolt. It also has AC coupling.